Review questions. What was Rutherford's main contribution to the study of atomic structure? I know you don't have your homework in front of you, but just let's dialogue for a little bit. Feel free to short answer. If it gets too many people responding, which tends not to be the problem in here, I'll kind of ask for hands again. But until then, and don't answer every question. Give your classmates a chance if you're a continual answerer. So what was Rutherford's main contribution to the study of atomic structure? Okay. Many of you put down the discovery of a particular particle, right? The discovery of that particle, and Rutherford was involved in the discovery of which particle? Pardon? No? Okay, proton. Remember, Crook and Thomson, they were about the electron. Rutherford came along, discovered the proton. So some of you had answers that related to the proton or discovery of the proton, and that's partially true. That's one of the stepping stones. But Rutherford's primary contribution was the development of the nuclear model. Sometimes we also have planetary models in there, right? This idea that there's a nucleus, and in the nucleus, that's where the protons and the neutrons are clustered closely together. And then outside of that nucleus is the domain where the negative electrons exist. Because remember before, the plum pudding model, where he built from, the plum pudding model said, this whole thing is basically positive goo with chunks of negative in it. And they were evenly distributed. What that means is that there was a net neutral charge all over the place, because anytime you were in one place, you were being equally attracted or repelled no matter where you were. But Rutherford's discovery of the proton said, no, wait a minute. The only thing that explains my results is if all the positives are clustered in the middle and all of the negatives are orbiting or existing outside of the center, the nuclear model. Okay. Here's a tough one. What do we call the apparatus that William Crookes used? The Crookes tube, right? Who's buried in Grant's tomb? Okay, William Crookes used the Crookes tube, and what did he discover with it? They called them cathode rays, which later he referred to as corpuscles, but you call them electrons. Okay? Number 3. If two electrically charged particles repel one another, what can be concluded about their charges? Yeah? They're like charges, right? Remember, like charges repel, opposite charges attract. So if two particles repel each other, they must have the same charge. This shows two negatives. It could likewise be two positives. But if they're like, they repel. If they're opposites, they attract. If a substance has 9 positive and 11 negative charges, is it, I should say, not it is it positively charged, negatively charged, or neutral?
Negative.
It is indeed negative, right? Remember, a balance, to be neutral means you've got a balance. This thing is out of balance. It has 9 positive, 11 negative. In this case, there are 2 more negatives than positive. It has a net -2 charge. 9 positives, take the 9 negatives to balance it out, good. Now we got 2 more negatives to account for. If we added another positive, it would be a net -1 charge. If we added 2 more positives, it would be 11 and 11, it would be a net neutral charge. Remember that every piece of matter has electrical charges. The question is, are they balanced or not? That's why when we talk about the atom, we talk about a balanced charge, meaning the number of electrons is equal to the number of protons. So it has a net neutral charge. Later on, we start talking about ions, and that's where there's going to be a net positive or a net negative charge, not balanced. And that's where chemistry happens. Right? So it has a net 2 negative or -2 charge. Give the location within the atom for a proton, electron, and a neutron. Of course, you could be real literal and say, according to which model? But according to our current thinking of the atom, where are the protons, electrons, and neutrons located? And we've already said it once when we talked about Rutherford's model, right? Remember, going back to this, that the protons and the neutrons are clustered close together, tightly packed in the center, the nucleus, and that the negatively charged electrons exist outside of the nucleus around that nucleus. That's true. See, here there was just one contiguous piece. Here it's positive with chunks of negative. Here it's protons, neutrons in the center with electrons orbiting. Here it's protons and neutrons in the center with electrons orbiting. Here it's protons and neutrons in the center and electrons in orbital clouds. But every one of them has protons and neutrons in a clustered tightly in the center and electrons existing outside of the nucleus. Okay. Number 6, why is it so hard to separate one isotope from another? And remember here we're talking about, we use the example of the nuclear bomb on how it's so difficult to enrich uranium that you need a certain percentage, and that the key to making a nuclear bomb is not building the casing and all that stuff. I mean, the mechanical pieces of it are kind of easy to do. It's the fuel that's hard to get. It's the isotope enrichment that's hard to do. That's the secret to making a nuclear weapon. Yes, ma'am?
I don't know if this is right or not, but is it because they behave identically?
Chemically, they are identical. That's right. So isotopes behave chemically identically. So it makes them nearly impossible to chemically separate. Remember the way you can separate out the different things? Let's say we've got isotopes of uranium. For us to separate them out, we have to do that either physically or chemically. Well, physically, they're all the same except for one more neutron. We don't go to tweezers, right, and separate them out. There's no filter we can use at the atomic level to filter them out. So we've got to attack this thing chemically. Oh, isotopes of an element behave chemically virtually, we'll say virtually, identically. That's why it's so difficult to make enrichment. It's so hard to get the proper isotope and filter it out and then add it to a sample to increase that percentage, because they behave identically. Remember I said that chemistry is primarily about the interaction of valence shell electrons. Well, these isotopes, they all have the same electron configurations. And now you know what electron configuration is, right? They all have the same electron configuration. And if chemistry, an interaction of things chemically, is based on electron configurations and they're all exactly the same, it's hard to differentiate them. There's not simple ways that we can pick them out. Therefore, we can't increase their concentrations easily. 7, what are the differences between the plum pudding model of the atom and the planetary model of the atom? And we've been kind of hitting around this whole thing all along with these answers, right? How did you say it? Go ahead.
But the plum pudding, the electrons are just there, but like after the nucleus broke, the planetary, the electrons orbit around the nucleus.
Yep, same thing. We've hit it several different times. In plum pudding, it's all positive with negative chunks, with the planetary concentrated positive in the middle and neutral, with electrons, the negative, orbiting on the outside. That's right. What is meant by the saying that wavelength and frequency are inversely proportional to each other? And again, don't worry about getting the technically right answer.
One is large, the other is small.
Right. So they respond in opposite directions. As one increases, the other one necessarily decreases, and vice versa. Remember, we looked at this chart here, and I used this little way of communicating that. Here we have a large wavelength over here at the AM side with the Roy G. Biv, if you look to the left, okay? So this kind of shows that over here the wavelengths are longer. The distances between peak to peak, or trough to trough, or equilibrium to equilibrium, ascending or descending, they're the same. I mean, excuse me, they're longer over here, longer wavelength, shorter wavelength. But this is a higher frequency, more cycles per second. This is a lower frequency. And because they're related, the product of those two things has to equal the speed of light. It's a constant. That means when one goes up, the other one has to go down. You know, when you're doing your multiplication tables. A times B equals 12. Well, when A is 1, B is 12. When A is 3, B is 4. When A is 4, B is 3. When A is 6, B is 2. When A is 12, B is 1. You know, they go in opposite directions because they have to equal the same thing. They have to equal a constant. So when one goes up, the other one necessarily has to go down. And that's the inversely proportional. It's kind of like the more money I give you, the less money I have. If there's a one amount, Say there's a certain amount of wealth in your family. Every time your parents give you an allowance, they are less wealthy, right? As your wealth goes up, their wealth goes down. That's why they encourage you to go out and get money from somebody else, so that their wealth doesn't go down whenever you get your allowance. If you still get such a thing. I'm not sure. Let's see. Everybody good on that? So that's inversely proportional. If they're directly proportional, what does that mean? Inversely proportional, one goes up, the other one must go down. Directly proportional, when one goes up, the other goes up. They have the same relationship, and that's the relationship between frequency and energy. See, as frequency gets higher, energy gets higher. They are directly proportional. When wavelength gets shorter, frequency gets higher and energy gets higher. Those are inversely proportional. If you have an orange light and a violet light, which emits the largest wavelength? Okay, so what you would need to do is go to your chart, or remember it. Remember the method I told you, start long. This is wavelength, Roy G. Biv. Where's orange? Roy, R-O, right? Biv, where's violet? Wavelength, which one has the largest wavelength? Roy G. Biv. The longest wavelength is with your, is with orange, right? Red, orange, yellow, blue, or green, blue, indigo, violet, according to wavelength. So which has the largest wavelength? The orange. Which light has a higher frequency? Well, remember, wavelength and frequency are inversely proportional. So whichever one has the higher wavelength must have the lower frequency. So it has to be the other one. Or you could look at it and say, okay, Roy G. Biv, small frequency, high wavelength. Or if you want to be daring and use the other way, this is Roy G. Biv for wavelength. This is Roy G. Biv for frequency. Or excuse me, Roy G. Biv for frequency. I don't ever do it that way, so forgive me for a minute. Roy G. Biv for wavelength. Inverse would be Roy G. Biv for frequency. Higher frequency is violet, right? Because it has a lower Roy G. Biv for wavelength. Or just remember they're inversely proportional. So if one is a higher wavelength, the other one must be a higher frequency. And then the question is, which emits the higher energy light? Now you could remember that E equals H times F. The energy is Planck's constant times the frequency. But you could also remember that energy is directly proportional to frequency. So whatever has the highest frequency has the highest energy. Whatever has the lowest wavelength has the highest frequency, has the highest energy. Again, because of the way they're related. So, which emits the higher energy light? Violet. Violet has a higher energy because violet has a higher frequency. Violet has a higher frequency because you remember the chart, or because orange has a larger wavelength. So the other must have a higher frequency. Two light bulbs emit light of the same color. Stop right there. Same color. What do we know about those two waves? If they're the same color, they're the same wavelength. Another way of saying that is they're also the same frequency. Okay? So knowing that they're the same color, meaning they have the same wavelength, meaning they have the same frequency, one of them is brighter than the other. What can you say about the wavelengths and amplitudes of the waves being emitted by each? We've already said they're the same wavelength, they're the same frequency, because they're the same color. But the second part says, what can we say about the amplitudes? Remember we covered that in class with this little diagram here? If I took both of those waves and I were able to synchronize them and lay them over top of each other, this could represent both waves to a point in terms of this node, this node, this node, this node at equilibrium. They're going to have the same frequency, meaning they're going to have the same wavelength. However, there is going to be a difference between the two waves. If I put the first wave on here and I took the other wave, let's say I took the brighter light and I put its waveform on top of this one, how would it be different? Ma'am? have a greater amplitude, right? It would be taller. The brighter light would do something like this. Above, below. Above, below. It would cross at the equilibrium points at the same place, but the waveform would have a higher amplitude, meaning it would go higher above equilibrium on the crest, and it would go lower below equilibrium on the trough. So color is related to wavelength and frequency. Brightness is related to the amplitude. Brighter light, higher amplitude. Okay? Any questions on that? Does it make sense that two waves that have the same color have the same wavelength and frequency? So the other part was just remembering that brightness is a factor of the amplitude. The higher the wavelength, the higher the amplitude, the brighter it's going to appear. If an atom absorbs energy, what happens to its electrons? And then, we'll answer them both, if the atom is emitting light, what are its electrons doing? We'll go back to this diagram right here. If an atom absorbs energy, what happens to its electrons first? Okay, when an atom absorbs energy, that energy is going into the components. And we're talking about the electrons right now, right? What are the electrons going to do when they become excited? When you add energy to something, you excite it. Ma'am?
I was thinking.
Okay. Yes, sir.
Shoot the electrons like out.
Right. The electrons would become excited and they would move out to a higher energy level. So in this case, if we think about it as in this Bohr type of model, first energy level, second energy level, third energy level, and now that we've done this S, you could think of it as the S orbital, first energy level, S orbital, second energy level, think of it kind of like that. But the basic idea is when that electron absorbs the energy, it gets excited, and it's got too much energy, it can't sit still. It's on a sugar high, right? It's got to go somewhere. Well, where can it go? It's in a track. It has to jump to a higher energy level. It has to go up so that it can basically be in a state equivalent to the energy it has. It just received energy. It was in a ground state before. Now that it's excited, it can't stay in the ground state. It's got to move out. And that's what happens when it absorbs the energy. The electron moves to a higher energy level. However, within a fraction of a second, the electron returns to ground state because, like all matter, they're lazy guys, adolescent boys who would rather be on the couch than mowing the lawn. So they, as quickly as they can, go back to ground state. But they can't go back to ground state without making another change. And when they drop down to the ground state, what do? Dropping to ground state, or dropping to any lower energy level, for that matter, requires that they give up some of the energy. Some of the energy that they absorb to go up has to be released to come down. Remember, we can't destroy energy. We got to do something with it. And so when they drop, or another way to think of it, they drop because they give off energy as a photon of light. They emit light so they can drop. It's not they drop so they give off light. They give off light so they can drop. So they give off the energy as a photon, boop, and they instantaneously exist at the lower energy level again. So when an atom is excited because it's absorbing energy, the electrons are moving to higher energy levels. And then as soon as they can, they emit the energy back out as a photon of light, and they drop down to a lower energy level. Again, I know I'm kind of got to keep moving, but if you have questions, I really need you to stop me. But I'm hoping once I review this, it makes sense. All right, 12. What is the concept of ground state and why is it important in chemistry? And we just covered it, so I'm not going to ask you to go through that. But the ground state is the lowest energy state of any substance, and matter strives to reach that energy state. Matter wants to be, again, personifying matter. We know it doesn't really have an emotional desire to be, but it fits for us to say matter seeks ground state. It wants to be a ground state. It's going to figure out how to get there. The electron gets zapped with energy. It can't help but move to a higher energy level because it has more energy. But it wants to be at ground state. So as soon as it can, it gets rid of the energy in the form of light and drops back to the lower energy level, eventually reaching ground state. The three fundamental particles that make up the atom are the proton, neutron, and electron. Order them in terms of decreasing mass. If you found it in the book, it's just simply neutron, proton, electron, in that order. Think of it this way. The neutron is basically a proton with an electron. So we're not going to get into how it's actually made up, and we can talk about quirks and all these other things that happen inside the atom, subatomic particles. But one way to remember this is the neutron is basically a proton with the additional mass of an electron. Now here's the deal. The electron is 2,000 times smaller than the electrons, than the proton. So it's kind of like you've got this huge mass and you add a feather. If you look at a lot of charts and they say, what is the mass of a proton and a neutron? They list it as the same mass. Because even though technically the neutron has more mass to it, the factor is so small that it falls away when you talk about significant figures. It's just so small. It's within the range of error, you know? So if you look at a chart and look for the mass, if you Googled it, you might have found the same masses. That's because of significant figures, not because that's technically accurate. So the neutron has a larger mass than the proton and then the itty-bitty electron. Define and give one example of a physical constant. We had two of them in this chapter, in Module 3. Two physical constants. But what is a physical constant, first of all? A physical constant. You're turning. That's not good. It's a measurable quantity that doesn't change. It's the same all the time. Physical constants have a constant value. You can count on it. Say, what's the speed of light? I don't know, what day is it? No. The speed of light in air is 3.0 times 10 to the 8 meters per second. When is it not that? For our purposes, it's never not that. It's constantly that. So it doesn't matter about what day of the week it is, what season of the year it is, how you feel. Light is going to be the same. We had another constant that we used in this module. Do you remember? Something that it's given to you, but it's the same every time you see it?
I don't remember the name, but I just know it's 1.7 times 10 to the negative 17.
Planck's constant, E equals hf, right? H is going to be given to you, Planck's constant. Why is it called Planck's constant? It's constant. What's that mean? It never gives up, right? No. It means it never changes. Otherwise, it would be Planck's number that depends upon how you feel or what day of the month it is or what season of the year it is. No, it's Planck's constant. It doesn't change. So it's a physical constant. It's measurable and it's always the same amount. Describe what an orbital is. Yay! What is an orbital? Now, an orbital belongs to which model? An orbital. Correct, the quantum mechanical model. Up until now, they were considered orbits. And an orbit is a racetrack. An orbital, and I hope you think of this picture whenever you think of orbitals. An orbital is a region in space where an electron is most likely to be found. Most likely to be found. Will it necessarily be found there? Mm-mm. The probability of it being there is very high. The probability of it being somewhere else is much lower. As a matter of fact, when you map it out, the greater the probability, the darker it looks whenever you do a true model of probability. And we look at those probability models, the region where it's most probable to be are what we call these orbitals. And those orbitals are the S, the P, the Ds, the Fs, those orbitals. Okay? So an orbital is a region where the electron is most likely to be found.